Okay, welcome back. So at this point, we've defined all of the major important kinematics variables. We've talked about distance and displacement, we've talked about speed and velocity, and we've finally defined acceleration. And I guess we've also defined time, but that one's pretty easy to define. Okay, so far you've learned these definitions and some equations. I'm going to list out the equations that you know right now. So far, we've talked about an equation that I like to call the definition of velocity, and that is the rate of change of displacement over time. The equation there is v hat equals d over t. You could also call this the definition of speed, depending on if you're talking about speed or velocity, depending on if this is distance or displacement. That's the very first equation that we learned, v hat equals d over t. In the last video, we talked about the definition of acceleration, which is not the rate of change of displacement over time, but the rate of change of velocity over time. So while velocity is the rate of change of displacement over time, acceleration is the rate of change of velocity over time. It's how the velocity itself is changing. And our equation for that was A equals delta V over t. The acceleration is equal to the change in velocity over some time interval. And we rearranged that equation into the first kinematics equation, or the fiat equation, as some of my students like to call it. Vf, the final velocity, equals the initial velocity plus the acceleration multiplied by the time. Okay? And that equation kind of makes sense if you think about it. The final velocity is going to end up being whatever the initial velocity was, multiplied by how the velocity changed and for how much time the velocity was changing. I call this the first kinematics equation because there's two other important kinematics equations to know, and they work fairly similarly, and they involve the same sorts of variables that we have in these equations. They are the fourth and fifth equations down from the top, these two right here. So the first one always ends up getting called the distance equation, I think for obvious reasons, because distance is out front. D equals VIT plus 1/2 AT squared. In other words, VI multiplied by T plus, all these are getting multiplied together, 1/2 A and T squared. Okay? You have to make sure you understand that you copy down the equation exactly as it is from the reference tables. All right? If you miss the t here, you're not copying down a correct equation. So again, VI, make that a little clearer, that's an I, T, VI times T plus 1/2 A T squared. I is not a variable by itself. It is simply V initial. Okay? It's a subscript on the V. The third kinematics equation is this one. Vf squared equals Vi squared plus 2AD. This is another useful equation, okay? If you know these three equations, you can solve pretty much any kinematics question that we could ask you. You might have to use each equation more than once. You might have to use two equations. You might have to use one equation more than once in order to figure out a few different variables, but you can solve any kinematics question that we ask, okay? And if you notice, all these equations are missing a certain one of the variables. So let's say that you needed to find a distance. Well, then very obviously you wouldn't use this equation because it has nothing to do with distance. There's no distance variable in there. There's no distance or displacement. There's no d in there. Okay? If you were looking for the final velocity, you very obviously would not use the second equation. If you're looking for time, you very obviously would not use the third equation. Okay? So all of these different equations, they're used in certain situations. It's up to you to start to figure out, okay, which one should I use in different situations? Sometimes there's more than one you can use, okay? But often there's one that is not going to be helpful to you and you have to pick from the remaining two. Like I said, these equations can be used separately or together to solve any motion problem we will deal with in this class. You only need these three equations, okay? Knowing these are good too. Well, this is really just a rearrangement of this, and this is also good, okay, to know. Now, the reason we talk about the kinematics equations is we're going to get into some very specific types of motion. The first one we're going to talk about is free fall. The definition of free fall is that it is a state of motion in which the only influence on an object's motion at that instant is gravity. Now, there's a much better way to define this, but in order to do so, we actually need to get to the second unit. So this we'll have to do for now. If an object is in free fall, that means the only influence on the object's motion at that instant is gravity. It doesn't matter what happened to the object before, okay? It doesn't matter if it was kicked, launched, thrown, pushed, whatever. All that matters is at that instant, the only thing currently affecting the object's motion, changing the object's motion, is gravity. So before we get to whether objects are in free fall or not, we gotta make a little note about something that comes up a lot. You might say for most of the objects we talk about in this class, they'll be in free fall. Someone will usually say, but wait a second. All of these objects that we're going to see are moving through the air. So isn't there air resistance or drag? It's kind of like a type of friction. You guys know friction, it slows things down. Wouldn't that count as an influence? So yes, technically, unless an object is falling through a vacuum, either the object is in space or is in a vacuum chamber, or is on an atmosphereless planet. And I should define vacuum. Vacuum is the lack of any sort of material in a certain space. So not even air, no gas or anything. It's the complete lack of matter. Okay? So technically, unless an object is falling in a vacuum, which would occur either on an atmosphereless planet, such as, well, the moon's not a planet, but the moon is an example. Space would be considered a vacuum, or a vacuum chamber here on Earth where they've pumped out all the air. Technically, unless you're in one of those things, there will be very, very small amounts of what we call air resistance. And you can think of this as the little particles of air impeding the motion of your object that's moving through it. So you might say, well, don't those little pieces of air affect the motion, the object's motion? We call that either air resistance or drag. It's just a type of friction. However, for almost everything we're going to do in here, the amount of air resistance is very, very small. In other words, we call that negligible. Negligible is another word for small. And since it's very small, we get pretty good results if we ignore or neglect to calculate anything with air resistance. And I've kind of talked about this before. Air resistance is very, very tricky to deal with. We are not at a level in this class where we're prepared to deal with air resistance. So, thankfully, the amount of air resistance is typically very low on anything we're going to throw or launch or kick or whatever in this class, so we're going to ignore it, we're going to neglect it. It is so small that it is considered negligible and okay to just not analyze. We still get a pretty good representation of the motion. So, we've defined free fall, we've made our little note about air resistance, now it's time to look at whether objects are in free fall or not. Let's think about the following situations. Let's say we have a pumpkin that has been dropped out a window. We're going to do that very soon. We're actually going to drop a pumpkin out the window. Would the pumpkin falling out the window be considered in free fall? The answer is yes. Not when it's in the person's hand about to drop it, but just after it leaves contact with the person's hand and it is no longer in contact with anything else, it is considered to be in free fall. We're going to ignore air resistance for that purpose. So yes, it is in free fall. What about a thrown baseball that is on its way back to Earth? So it's gone up, it's reached the peak of its motion, and it's coming back down. The only influence on the baseball at that instant is gravity trying to pull the ball back to Earth. It doesn't matter that the person threw the baseball a couple seconds ago. That's true, and while the person was in contact with the baseball, it was not in free fall. But once it leaves his hand, on the way back down, it's not touching anything else. That is definitely in free fall. Here's where I usually get people. A kicked soccer ball that is still on its way up. I ask people if that is in free fall, and I usually get about half saying yes, half saying no. Those that say yes say that the soccer ball is only being affected by gravity at that instant. It's no longer in contact with the person's foot, and that's correct. Okay, this object is in free fall. The people who say no will say that, well, it's not falling, it's rising. That's not the definition of free fall. Free fall is specifically the only influence on an object's motion at that instant is gravity. The ball is still being influenced by gravity even if it's on the way up, because the ball is slowing down. Gravity is starting to try to bring it back to Earth. It doesn't matter the direction of motion. There's nothing in this definition about the direction of motion. It only says, is the object only being influenced by gravity? In this case, that's yes. So a kicked soccer ball that is still on its way up is also in free fall. Number 4 also gets people. The answer is yes. A football that is at the highest point in its movement, so it's been kicked or thrown or launched or whatever, that football at the very peak, at the highest it gets, is also in free fall. Gravity is still affecting it there. Gravity is trying to pull the football back to Earth. It doesn't matter that it's at the peak and that it's not moving, that it's not falling. That has nothing to do with the definition. At that instant, gravity is the only thing affecting the football, so it must be in free fall. So our conclusion here is that the object's motion does not determine if something is in free fall. Instead, what determines if it's in free fall or not is what influences that motion. If it's gravity and only gravity, then the object is in free fall. If it's anything else, then the object is not in free fall. So if it's still in contact with a person or an object, not in free fall. If air resistance is non-negligible, if it's if it's like, I don't know, it's like you were on a planet with a very dense atmosphere and that was obviously affecting the motion, then it would not be in free fall. Okay? Let's do some other examples of objects not in free fall. Let's look at a feather that falls. Now, you know most objects, when they fall, will just drop straight to the ground. What does a feather do? It will kind of drift around in the air. Now, most objects you can neglect air resistance for. Okay, almost 99% of the objects we'll look at you can neglect air resistance for because it doesn't really seem to affect it. Feathers, though, are a little different. They're very affected by air resistance. So we wouldn't say that gravity is the only thing affecting the feather's motion. In this case, gravity and air resistance both affect it, so we can say that the feather falling, at least in an atmosphere like we have on Earth, is not free fall because air resistance for that object is too big. Another example of an object not in free fall would be a ball on a ramp. You might say, well, wait a second, the ball is moving down because of gravity, why isn't that free fall? Well, look, it's in contact with the ramp. The ramp affects the acceleration. If you have a very shallow ramp, that would not be as high in acceleration, not as big of a change in velocity over time as if you had a very steep ramp. So the ramp influences the motion. A third example of an object not in free fall would be a person sitting in a chair, probably like you right now watching this video. Okay? It's true that gravity is acting on you. If it wasn't, there might be a case where you start to float up and away. However, you're staying on your bed, so gravity is affecting you, but also the bed is influencing your motion as well. The bed or the chair or whatever is stopping you from falling through and just being pulled down due to gravity. So that also influences your motion. Chair acts against gravity. Okay. So, when we talk about free fall on Earth, if we have an object that is in free fall, what that means is that the object will do something very specific. Objects in free fall accelerate. Remember, accelerate means change in velocity over some time period. So, if you drop an object, does its velocity change? Absolutely. Right when I let go of the pen, it wasn't moving very fast. By the time it gets towards the desk here, it's moving a lot faster. So gravity causes objects in free fall to accelerate or change their velocity. And the neat thing about gravity is that every object in free fall accelerates at the same rate. And that rate is a very, very special number in physics. That rate is 9.81 meters per second squared. It's a very famous number. This number is referred to as g, and that's the symbol for it. It stands for acceleration due to gravity. Okay, little g. Little g is on your reference tables. It's on the very front of your reference tables under the table of list of physical constants. It's right here. It says acceleration due to gravity. The symbol for it is g. The value is 9.81 meters per second squared. Make sure you don't confuse it with big G. We haven't gotten there yet. So even though it's an acceleration due to gravity, the symbol for it is g. Okay? And I should note that the direction of this acceleration, since acceleration is a vector, is straight down towards the Earth. And the best thing about acceleration due to gravity, if an object is in free fall, this again, if an object's in free fall, it will accelerate at this rate, 9.81 meters per second squared. The best thing about it is that as long as the object is dropped near Earth, and near Earth means anything, like even where planes are flying, that's close enough to near Earth since Earth is so big. Okay? The best thing is, as long as the object is near Earth, acceleration due to gravity is constant. It does not change. So the rate at which the velocity changes is a constant. That's a little confusing. The velocity is changing, but the amount the velocity is changing by each second is fairly constant. That's great for us, okay? That makes our equations and our math much, much simpler than if the acceleration due to gravity varied as it moved down. We would have to introduce even more variables. We'd have to talk about how the acceleration changes over time, but we don't. The acceleration for an object in free fall is a constant 9.81 meters per second squared. So let's look at some free fall situations here. Situation number one, we're just going to drop an object onto the ground. As you can see, we have a pumpkin falling, and we have different instances as it moves down. Okay? This is very similar to what we're going to do very shortly. At point number one, this is right after the pumpkin is dropped. It's basically right as the person releases the pumpkin. At this point, at image number one, there's not yet any velocity. Remember, it says the picture below shows a path of a pumpkin being dropped from rest to the ground. From rest means the initial velocity is 0. Positions shown at different times during its fall. We're going to sketch the velocity and acceleration vectors at each point. So there's no velocity, but we know that the acceleration is downward, points towards the ground. Now let's move on to time number 2. The pumpkin is moved down a little bit. That means it must have some velocity since it has some displacement from its initial position. So now we have some velocity. The pumpkin is moving downward, so the velocity is downward. It's not quite that big yet, but it looks like this. The acceleration, since the pumpkin is near Earth, is still going to be the same. So I'm going to draw that vector approximately the same size as I drew my first acceleration vector. So notice that the velocity is changing, but the acceleration hasn't changed. For point number 3, now the pumpkin's fallen a little bit farther, it's probably picked up some more speed. So my velocity vector is going to be a little bit bigger. Is that going to change my acceleration vector? Absolutely not. The acceleration is still about the same, or not even about the same, it's still exactly the same as it was. Notice that the distance the pumpkin falls between each moment in time is getting bigger and bigger. That's an indication that the velocity is getting bigger and bigger. It's traveling through a bigger displacement in a similar time period. So at point number 4, the velocity is really getting quite big by now. But again, the acceleration is approximately the same. By the time we get down to point 5, the velocity is really big. But again, as the pumpkin is still in free fall, even when it gets towards point 5, the acceleration hasn't changed. Okay? So, if you have an object that's in free fall, the velocity will change, okay? That's what acceleration means. If it has some acceleration, that means the velocity is going to change. But the acceleration itself does not change. It remains constant for the entirety of the object being in free fall. So again, for our conclusion, for a dropped object, A is constant. And that's because A is equal to g, the acceleration due to gravity, which is constant for objects in free fall, and directed downward. The velocity, on the other hand, increases in the direction toward the ground. V got bigger and bigger, and it kept pointing, and it was pointing towards the ground. A remained the same, and was pointing towards the ground. Again, from one of our last videos, notice that because the velocity and the acceleration were in the same direction, the object sped up. The velocity got bigger and bigger. Okay? We're going to do some math. We're going to try out those new equations now. If it took the pumpkin 2.4 seconds to hit the ground, determine both the final velocity and the height from which it was dropped. Well, final velocity, that's pretty easy to find. We could have done that last time. We know that it took the pumpkin 2.4 seconds to hit the ground. We know it was dropped from rest, so VI is 0 meters per second. We want the final velocity, question mark, and we know the acceleration is 9.81 meters per second squared towards the ground. What we don't know, also I should list out, we don't know the distance that it falls, but that's what we're going to find later, the height that it was dropped from. We can find the final velocity by using the Fiat equation, because we know that VF equals VI plus AT. The initial velocity was 0, final velocity must be equal to 9.81 meters per second squared multiplied by 2.4 seconds. So the final velocity is 9.81 times 2.4. The final velocity is 23.544 meters per second. Okay? Now, as far as finding the distance, we could use either of the equations we've talked about so far. I'm going to use the distance equation, or what I call the distance equation, the second kinematics equation. D equals VIT plus 1/2 AT squared. Now, interestingly, because the initial velocity is 0, it doesn't matter that the time is 2.4. Anything times 0 is equal to 0. That doesn't mean the time is 0. It means that this term, VI times t, the whole thing, is just equal to 0. That doesn't affect the time. Okay, I still have a time variable over here, and that's still 2.4. But 2.4 times 0 is 0, so I can just cross off that whole term and write 0. So my distance must be equal to 1/2 times 9.81 meters per second squared multiplied by 2.4 seconds squared. Do not forget that squared. That's very easy to forget. I'm going to start with that. 2.4 times 2.4, 5.76, times 9.81, times 1/2. The distance that this pumpkin must have fallen is 28.25 meters. So we can use those other kinematics equations to figure out more than we could have if we just knew the Fiat equation. So now we know the height from which it was dropped. The pumpkin must have moved to a little over 28 meters in this period of time. Okay? So far we've talked about the basics of free fall. We've looked at an example with a pumpkin falling from rest. We're going to look at some more free fall examples in the next video.